Good morning, good afternoon, and good evening, everyone. So today we're going to be continuing our applied linear algebra series and numerical analysis, and we're going to do some exercises on homework one. So what I plan to do here is I'm going to make it super quick. I just want to get the key ideas of how we can solve these problems. So let's just hop right into it. So here we have these two vectors. So we have f and g, and they have these components, and we're going to compute the coordinates of each of these vectors with respect to basis vectors, right? So let's try. So here's what I'm gonna do. Let's actually look at this conceptually. Like what do these mean? Well, first of all, we have these vectors, right? And then we want to compute the coordinates of these vectors with respect to two vectors. So if we have two vectors, how do we find the other vector? That's what that's telling us. Okay. And so how do we do that? Well, it's actually just we want to find a linear combination of the two basis vectors that will give us the other vector that we're looking for. And that's how we compute the coordinates. So the idea, here's the bottom line. So the idea is to to get, say, that vector f, and we want to see if we can write it as a linear combination of these other guys. Okay. And if there is a solution, so if there's a number for alpha 1 and 2, then those are the coordinates with respect to what we have. Okay. So let's try. So for instance, let's just do example one. I'm just going to keep this as short as possible. So example one tells us that we want a linear combination of these guys here. Uh-oh. Huh, funny enough, OneNote is not responding again. Okay, yep, OneNote is down. Okay, we'll wait for a bit. We'll see. Okay, there we go. So E sub 1 is 1, 0. Added to this guy. And we say that this is equal to that first vector. I can't see the vector. I think it was 1, 3. Yeah, it was 1, 3. Goodness me. Wow. Okay. Uh-oh. 1, 3. And apparently we do have solutions for these. Alpha 1 is equal to, if I'm not mistaken, yeah, alpha 1 was 1 and alpha 2 was 3. So that means we can write f as a linear combination of e1 plus 3 e2. And so what does that tell us? That tells us to get the f based on the standard basis vectors. To get the f, we need to go 1 to the right and 3 up. So how would that look like? We have the standard basis, right? So that's this 1, 0, 1, 0. I'll write it in row. This is 0, 1. And we want to get to 1, 3. So we go 1 and 3 up. So this would give us that point. And we say that that's how we get there, to that f. This here is F. And this has, 1, 3. So another way we can look at this is the basis coefficients. That will tell us how to get to that vector F based on the standard basis vectors, based on the two vectors that we have. And it's the same idea for B to D. Okay. Let's look at number 2. So that was pretty easy. So given sets of vectors, which of them span R2, which are below the span of R2, which are the span of R3, which sets form a basis for R2, and which sets form a basis for R3. Let's actually try to go through this one by one. Here we see that these two are linearly independent, linearly dependent. There's a linearly dependent set because the second vector is just 3 times the first vector. So we can write this, say V1, as a linear combination of, actually, yeah, we can do, say this is V2. The second vector is just 3 of V1. So it's V2 is a linear combination of V1. Okay, the way we check if they span something, well, we put it in matrix, right? So if we put this in matrix like this, and we convert it to echelon form, we would get something like 1, 3, 0, 0. And here we see that there is a pivot. There is no pivot every row, and there is no pivot every column. If there is no pivot every column, the column vectors are dependent. And so, yeah, we're right, they're dependent. And there is no pivot every row, so they don't span R3. R2, my bad. They don't span R2. These sets of vectors don't span R2. Well, now what do they span? They span a line, right? So here, this thing doesn't span R2. No span. Not span R2. Definitely not span R3. Simple reason, we have the number of components is not 3, it's only 2. Do they form a basis for R2? To form a basis, we need 2 criteria, right? So to form a basis, if we review that, to form basis, we need 2 things. One is linearly independent set of vectors. Are they linearly independent? No. So that checks out. Do they span R2? Because we're asking for basis for R2. So do they span R2? Well, no. So they are not basis for R2. They don't form a basis for R2. Okay. So not span, no basis for R2. We can try these other ones, but yeah, we can try the other ones. It's fine. But here, so no pivot every row, so they don't span R2. No pivot every column, so dependent set. And so they don't form a basis. Okay, let's try number 3. So we let V, so 1, Vn to be spanning set in Rd. So that basically means you have the span from V1 all the way to Vn that's equal to Rd. Is that true? Actually, no, that's true. Their span is in the dimensions. So we prove that, okay, for letter A, the dot product of x and v is 0 for all v and Rd, then x is 0. So our proof here is that, okay, we assume that their dot product is 0. So that means, what can we say about it? X and v are orthogonal vectors. They're pairwise orthogonal vectors for all v and Rd. And here we define x to be in Rd so that this thing works. The dot product of these two vectors are defined. And because the dot product of x and v is 0, we say that we take x to be v. And so, well, if we do the same thing, we get 0. Another way of writing it is the norm squared of that same vector x. And this is only true if x is 0. So that's how we went from explaining this thing to this thing. So really, proof is all about explaining why things work. Okay, that's what proof is. It's not these complicated math formulas. Well, there are complicated math formulas, but it's more really about explaining why something's true. Okay, let's do b. So we have x, v sub k to be 0 for all k1 to n, then x is 0. Then we say, or here we say that the span of v1 to vn is Rd, right? And we write v to be a linear combination of some scalar c and then v. So here are the components, right? We can do that. And then we say that xv, this dot product of this guy, is the same as x, and then this linear combination to get v, right? Okay, I hope this is making sense so far. But basically, we're saying that this is in the span of v1 to vn, right? And by linearity, we can put the summation along with the scalar outside. Okay, so that's something that we can keep in mind. We can put this outside. How do we know? Well, I think we did this. Linearity. We did talk about what linearity is. It was something like the. I forgot that. It was. I proved it. It was a while ago when I proved that. No, it wasn't a while ago. It was just this morning. That's too much stuff to remember. Okay, where can I find it? No, it's not that one. Where's linearity? Huh. Oh, there you are. This u alpha v plus w is the same as alpha uv plus uw. We did have a way of proving that idea. Actually, you know what? I think we can do it without even just going through the definitions. I think we can do it. Let me try. See if we can do this. How do we say that these two are equal to each other? Well, a way. Let me see. Let me try. Let me try. Say we have this x. We have this summation. Let me just go here. We have n. I'll do j. Why not? Cj, bj. Now I think, yeah, these are referring to vectors, right? So we know this is true from x and v. Okay. Now how can we prove this? Well, we can say this is the same thing as x. C1 v1 plus all the way to n vn. And then what can we say about this idea? Well, when we add it, how would that look like? This is the same thing as a dot product if we think about it. We're multiplying c to v. This in and of itself is a dot product. So I would say a c vector and a v vector. Huh, can we do that? Let's try. I feel like I'm messing up. What else can we say about it? How did this go here? That's the funny thing. No, no. Okay, this is extra weird. I don't know why. Wait, I'm gonna go back. I know I proved it at some point. I just forgot where. It clicked though. That's the thing. Are you? Oh, there you are. Oh, you did a summation of all of these guys. Okay, so that's what you did. So we did a summation of all of these guys, and I somehow managed to land on that. I see. Okay, let me try. So again, we have this idea. Then the way he did it was he did that, and then you would do another summation based on this. So you do something like j is 1n. You would say something like xj, and then you would do something like you would do a vj. God, how did I prove this? Hmm, what? Okay, now I'm confused. I forgot how to prove linearity. I was able to do it if you give me a vector. I wasn't able to do it here. Or maybe I have to simplify it. I think. I think I have to simplify it. So somehow he was able to do it. Oh, he did this. Oh, I see what he did. Multiply that here. Okay, okay. Let me see. And then he added it. Okay, let me try. So he, he's doing VJ. Now I don't know what VJ is. VJ is this guy. Oh, that's funny. And then, oh no. Great, I'm lost. Fine. No worries, you got time. Let me try it again. Great, now my OneNote's not responding. This is very cool. OneNote is not responding. I think I just broke the system. Maybe do X, and then I think we can just do C1 V1, C2 V2, all the way to Cn Vn. And then, oh, what can I do? Can put them all in a summation, why not? Oh, I know what we can do. We can do this. Oh, shoot. Oh no, I could factor out the CJ. Wait a minute. Or, huh, could factor this one out. So I would do like CJ all the way to N, then VJ. Okay, I just switched it out. I'm trying to play around with it. I'm seeing what I can do. How the hell did I do it? Oh no, but that one was a vector. That's the thing. So it wasn't okay. I think that one was easier because that one was a vector. So I think I'm just wasting my time doing this. Yeah, those were vectors, which I could just translate into summations. Yeah, these were vectors. So where are you? I know I proved it somewhere. I just forgot. Oh, there you are. Yeah, so these were vectors. And then you could somehow just sum everything up. This is linearity. And then if you do that, you somehow get this value, which is funny because I didn't get this value at all. Yeah, so apparently, okay, I give up. The idea is that we can actually take out the C and it would still be the same thing. The one with the C and the summation, we could take that out. It would still be the same thing. So if I take out this summation with the C, I would still get the same thing. And that would be a 0 because my XVI, dot product of that is just a 0. So everything's just going to be 0. And there we have it. XV is 0. So that's linearity. And then C is xvk minus yvk is 0. For all k, then x equals y. So x minus yvk. So here we just subtracted it. Because we can do that, right? The way we think about this, we can actually think of it as column vectors, such that if we just subtract them, it would just be a 0. So we say something like x minus y is 0, x equals y. So that one's not an issue. And now to prove this parallelogram identity, well, I would just go through the whole thing. So I would say something like, okay, we have this. So this one would just be a way to write it is this vector xy. That's the same thing. We add it to a vector x minus y. And then we would get that. And now how do I go about this idea? Well, I could multiply 1/2 to all of them, right? So I would do something like this. And then 1/2 to this. Now I could even do it to all of them. That's funny though. I don't think that'll work. How did I do it? Oh, so I distributed this idea. So I did something like, okay, so I did 1/2 of something. So here when we, oh, I did summations basically. Uh-oh. Ay, ay, ay. Yeah, I would do summations here. This is the same thing as doing a summation j to n. We would do something like x plus y. I would square that. Xj. We square that. This one, x1 y1. Oh yeah, and then we would square it, yeah. And then we just continue doing that. We have this other idea here. We square that. And then what else can we do? We can factor it out. So we would get something like, completely ignoring the summation idea, we're just gonna do xj, yj. So we would do x squared j plus 2xj, yj plus yj squared. Then we add that idea, this other one. This is just xj squared minus 2xj, yj. I forgot. Oh, we added, yeah. And then plus yj squared. And then from there, well, we could now combine these stuff. Yeah, so I would just add all of them in one go, if that makes sense. Or better yet, I could just put them all one thing. Okay, here's the idea about summations is that I could do it for every term. So I'm actually going to do it for every term. I know. I would put this thing out though. I'm trying to focus on organizing this and making it into vectors. So I would put this guy out. Then we do xj, yj. Then we add it again with another summation, yj. And then we would add it again with another summation, xj minus 2 of, then we do xj, yj. Then same thing again. Okay, but basically that's the idea, right? Uh-oh. No, we're getting it though. We're like separating the terms. And from there, we actually just get, this one's the same thing as this. This one's the same thing as this. Oh no, I did not mean to do that. Uh-oh, that was my bad. Oh my, OneNote is not responding. This is just great. Yeah, maybe I should get a better laptop next time. Or I should just get something here. I'm gonna hope we actually get to the vector. We get to the solution. Let's see. So here we get xy. This is the same thing as yy. Here we add it again, so we get xx. Here we get minus, minus 2xy plus yy. So that's what we got. And we keep going here. So we say, and we actually can just subtract this idea. Oh, here we get 2xx plus 2yy. We could cancel out that 2, so we just get xx, yy. And this is just their norm. We proved it. Done. Nice. Okay, so I think that might be it. Yeah, so that's all for this video. I hope you guys enjoyed. And I'll see you all in the next one. Actually, I'll tease the concept a little bit. Okay, I'll put another, this is annoying, but I'll put another tab here. OneNote is not responding for some reason, and I don't know why. It's just not responding. It's kind of annoying, to be honest. So I have to do something about that. But yeah, but there's something about this that's not working. Is it just me or hack something? I don't know what's happening. Okay, but the next lecture is going to be 7. Interesting. We're going to take a whole day to do this. I'm going to do a new one of just me going through this idea. I think, yeah, we're now at 7. Okay, so this is a better one, yeah. Yeah. I hope this, okay, this should be easy. I hope. If not, then that's just stupid. Now, this might be a breeze compared to the other ones. But we'll see. I'm not gonna say too much. Right, so lecture 7, we're mostly going to be talking about intro to matrices. So what are matrices? And as well as linear equations. Now, what are these? Okay. Right. So I hope you guys enjoyed the video, and I'll see you all in this next one.